All right, now that we've got the molecules that we got from our fossil fuels physically sorted out, now it's time to chemically process them. And the reason we were going to do chemical processing on them is, one, it may make that into something that's more useful for us, or something that works better. Let's put it that way, I guess. So if you think back to the fractional distillation tower, every barrel of crude oil, depending on the well you're getting it from, is slightly different. It might have more different parts of the mixture. So some is very thick and tar-like, and maybe we don't get as much like gasoline type stuff out of it. And some of it's more watery, and we get less of the tar and more of the other stuff. But either way, if you think about the global demand, we don't need a whole lot of like tar and fuel oil compared to what we would need for something like maybe gasoline. Like the demand is not nearly as high. So the chemical processing allows us to take some of those big molecules that maybe we don't need as much of and turn them into smaller molecules that we want more of, that we have more use for or more demand for. So there's three types of chemical processing we're going to look at. There's cracking, catalytic reforming, and alkylation. And each of these is, again, trying to turn this into something more useful for us, but they're doing it in different ways. So we'll look at each one a little bit separately. So let me jump to the whiteboard here. The first one is called cracking. And cracking is taking, and here's the big picture you need to know, taking a big molecule and breaking it into smaller ones. So let's say I started with a molecule like C7H16. So we have a heptane parent, and maybe I don't want that, or I need something else. So we're going to crack that molecule into, let's say, a C3H8, a propane, and maybe another propane. And those are more maybe useful or beneficial to us. Now you'll notice though, I've used up all the hydrogens. I started with 16 H's and I ended with 16 H's. But I've only used 6 of the carbons. So one of the byproducts sometimes of cracking, depending on the method they do, is you're sometimes also left with just this solid carbon, and we call that coke. It's just kind of a solid carbon residue that's left over. Now there are ways to get around that, I'll show you in a second, but that is one of the byproducts you can get from this process. Now that could still be collected and used for other processes, but it would be some leftovers. It doesn't have to be a perfect break, like this one I did an even split, but you could do something like C17H36, and we could break that molecule into a C9H20 and a C7H16. So now it's not a quite even break. It doesn't have to be. Cracking just means big breaking into small, even if they're uneven. Again, in this case, we would still have that solid carbon residue left over just because of what we did. Now, the way they can sometimes get around that is called hydrocracking, where they add in hydrogen gas to the process to help this out. So for example, if I took C10H22 and added some hydrogen gas to the process, that would allow us to make, let's say, C5H12 and C5H12. 2 molecules of pentane. But now I had enough hydrogen that I didn't end up with that carbon residue. I could end up with 2 alkanes. Now usually in order to do this, you have to have just the right mixture, especially if you're trying to get a very specific molecule that you want it to break into. You have just the right temperature, just the right pressure, quite possibly a different catalysts that allow this to happen a little bit more efficiently. But that's cracking in a nutshell. We're trying to manipulate those variables, find the right catalyst, temperatures, pressures, whatever it might be, to get these big molecules that we don't need as much of to break into these smaller ones that maybe we have more use for. Okay, so that's cracking. The next one is catalytic reforming. And that's where we're going to use usually really high heat, very high pressures, and quite often a catalyst to reform a molecule. We're not snapping it this time, we're just mushing it around and changing its shape. Specifically, we're trying to change a straight chain molecule into an aromatic molecule. And the reason is because they burn better, especially in the internal combustion engines that we use them in, like cars and lawnmowers and things like that. An aromatic molecule burns better than just a straight one. So in this example, you would take something like, oops, excuse me, this 7-carbon molecule here. So this is a heptane molecule. And we would use heat, pressure, catalyst. So sometimes we can list that here. Heat, pressure, catalyst, whatever those conditions might be. And we're trying to turn it into an aromatic molecule, which, remember, means it contains benzene. So in this case, we'd end up with a methylbenzene or a toluene molecule here. But if you remember back, benzene doesn't have a lot of hydrogens on it. It's only C6H6. And so that would even lose one because of the methyl branch. So there's really not a lot of H's there. So this process also is going to produce hydrogen gas as all those H's come off in order to turn it into this aromatic molecule. So we'd probably also collect that hydrogen and use it for something else as well. So that's catalytic reforming. Straight molecule over there gets turned into an aromatic molecule up here because it burns better. The next one is alkylation, and I'll leave it on the same line here. So let's say we've got the same molecule to start with, our heptane. And under just the right conditions again, but now instead of turning it into an aromatic molecule, we're trying to increase the amount of branching. Again, because it burns better. Big, long, straight molecules don't burn really great. Taking that molecule and making it a smaller molecule with more branches burns a little better. So in this case, we could turn that straight heptane into a pentane, maybe that had a couple of methyl branches on it. That would burn a little bit better, a little bit more efficiently. Okay. So those are the chemical processing that you need to know. There's cracking, to take big and turn it into small. Catalytic reforming is the top one, where we took a straight molecule and turned it into an aromatic so that it burns better. And there's alkylation. Remember that alkyl, that YL means branch. That might help you remember it. Where we take a straight chain molecule and we turn it into a more branched molecule so that they burn a little bit better in our engines. Okay. Now, the last part here in your notes, you don't need to know. It's just talking about octane. And that molecule on the left is called 2,2,4-trimethylpentane, and that's what we set our octane ratings as. So when you go to the gas pump and you buy 92 octane fuel, what that means is you're burning fuel that burns 92% like that 2,2,4-trimethylpentane molecule. The heptane molecule that's right beside it in your notes would have an octane rating of 0. So we want it to be more like 2,2,4-trimethylpentane, less like just straight heptane, so that it burns better in your fuel. So if you buy regular gas, that's probably between an 89 and a 92. If you buy premium gas, then you're looking more like a 96% or a 96 octane, which is really a 96% like 2,2,4-trimethylpentane. You don't need to know any of that octane stuff. I just thought it might be interesting for you to look at. Now, let me just show you this as an example at the end here. This is how this whole thing might work in a refinery. So you see the crude oil on the side. It goes into the boiler where it's heated up to just insane temperatures and then put into the fractional distillation column. And as it works its way up, it cools. And as things can't stay gas anymore because they've cooled off too much, Just like if you've got steam coming off of a pot, when it cools off, it turns back into water droplets. They turn back into liquid and they are collected. But you'll see here the different mixtures we can get, and these numbers here are the number of carbons that would be in that molecule. But you'll see here the lubricating oils and the heavy gas oils, we probably don't need those a lot. So they go first to this cracking unit. And that cracking unit is going to take the molecules, those big molecules, and snap them into smaller ones so they can be turned into things up at the top, like a naphtha mixture in this case, or maybe even a gasoline. And you'll see it also, there's a catalytic reformer up there that would turn those into aromatic molecules that are going to burn a little better. You can see the coker here that's probably going to take some of that coke residue and things like that. There's an alkylation unit that's going to be adding branching onto those molecules so that they burn a little better to make this gas oil or diesel right here. But it's probably a whole bunch of these different processes all working together to take the crude oil from whatever source you're getting it from and turning it into whatever's in demand, whatever you want to sell, be it gasoline or kerosene or diesel or fuel oil or whatever that might be. It's going to be a combination of all of those physical and chemical processes going on to get that mixture turned into what we want it to be in the end. Okay? So if there's anything there that gives you trouble, let me know. Remember, that first video was the physical processing. This video is all about the chemical processing, turning something not chemically from this molecule into a new molecule, whether that's a new shape or a new size or whatever. But we have changed the molecules. The physical, we didn't change them, we just sorted them out. Okay? If you have any trouble, let me know.